In this video, we're going to talk about friction and how it relates to kinematics or motion equations. Let's start by writing out our friction and force equations. We know that all the friction equations sort of follow this form, mu times normal force, because friction is fun. So for static friction, we know that static friction, or Fs, is always less than or equal to the maximum static friction, which is equal to the static coefficient of friction times the normal force. Kinetic friction is a value that does not vary, and it is simply always equal to mu, or the kinetic coefficient of friction, times the normal force. So these are our two friction equations. Now, force relates to motion through our net force equation, sigma F equals ma. There we go, that's a better sigma. So in almost every problem, we're going to draw a free body diagram and try to understand or identify what the net force is. Using that, we will be able to relate it to acceleration. Now, the motion equations that have acceleration in them are v equals at plus v naught, x equals 1/2 at squared plus v naught t plus x naught, which of course you could use for y, and then v squared equals 2a delta x, which you might prefer to write as x minus x naught plus v naught squared. So somewhere in your paper, write these equations very, very big so that you can go back to them and use them to solve various friction problems where something is accelerating, or meaning speeding up or slowing down. Let's do a couple of examples. You push a 25 kilogram cardboard box from rest across a concrete floor with a constant force of 400 newtons. The kinetic coefficient of friction between cardboard and the concrete is 0.4. The static coefficient of friction between cardboard and concrete is 0.5. What is the velocity of the box after 10 seconds, and how far has the box traveled in 10 seconds? Okay, so the first thing that I need to do here is take a look at the kinetic and static coefficients of friction. So I'll write those down. Mu k is 0.4 and mu s is 0.5. Now, before I even try to solve this problem, since it's being pushed from rest, there's a chance that this box actually doesn't move at all, and that this 400 Newton push is not enough to get the box moving. In that case, the answer to A and B would just be 0. So let's figure out first, what is the maximum static friction force? So remember, that's what we use mu s for. We use mu s times the normal force. To figure out what the normal force is, I'm going to think about this problem and draw a little free body diagram for the box. There will be the weight force down, normal force up, applied force to the right of 400 newtons, and then some force of friction back, which is either going to be K or S. We'll find out as soon as we calculate the maximum static friction. So we should be okay with the fact that the normal force is equal to the weight in this problem, since the box is not on an elevator accelerating up or down, which means I can say that N is equal to mg and replace that in my friction equation. So now I can calculate the maximum static friction. 0.5 times 25 kilograms, and we'll use 10 for the acceleration due to gravity to speed the problem up. This gives me 125 newtons. Okay, so why did we do this? Well, we know that the applied force is 400 newtons, and the box started from rest. So if the applied force was less than 125, the box simply wouldn't move. But because this applied force is more than 125, then it does, in fact, move. So what that tells us is that while this box is moving, there will be kinetic friction. So now that we've used the maximum static friction, or we figured out what it is, we actually don't need it for the rest of the problem. So I'm going to erase it. Okay, so we know that the applied force is 400 newtons. And now what I can do is I can figure out what is that force of kinetic friction equal to. To do that, I would say the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, which again, we already discussed is equal to the weight, or mg, in this problem. So now I can plug in these numbers and get a value. 0.4 times 25 kilograms times 10 meters per second squared, which is 100 newtons. Okay, so I've figured out what the force, or that there is kinetic friction acting on the box, and now I know that there's 100 newtons, which maybe I'll draw my friction force much smaller than that 400. So how do I use this information to figure out the velocity of the box after 10 seconds, or how far it has traveled? Well, I can use this 100 newtons and the applied force of 400 newtons to get the net force. The net force is always equal to mass times acceleration. Remember that that's like our key. And I know that in this problem specifically, the net force is the applied force F minus friction. So 400 newtons minus 100 newtons, or 300. Using that net force and the mass, I can get the acceleration. So to do that, I divide both sides by m. Remember, so the acceleration is equal to the net force over the mass. So 300 newtons divided by 25 kilograms, which is a number that I'm thinking is 12. 12, yeah, okay. 12 meters per second squared. Okay, great. Now that I've found the acceleration, I can start looking at my motion equations to see which one I need to use to find the velocity of the box after 10 seconds and how far the box has traveled in 10 seconds. Again, I'm going to kind of clear up some space so it's easier to see what I'm doing and erase a few things. Okay, and we need to remember that the acceleration we found is 12 meters per second squared. Okay, so now let's focus on this box. First of all, the fact that it moves from rest tells me that v naught, the initial velocity, is 0. And part A wants me to find the final velocity after 10 seconds. So it gives me t equals 10 and asks to find v. So I take a look at my motion equations and I think, which equation has v, a, t, and v naught in it? Well, the first one. So I go back to my problem and I write it down. V equals AT plus V naught. I don't have to rearrange anything because it's already going to tell me the final velocity. So 12 meters per second squared times 10 seconds plus the initial velocity of 0, which I could have gotten rid of that in the beginning if I wanted to. So 12 meters per second squared times 10 seconds is 120 meters per second, which is blindingly fast, and you definitely are getting close to a takeoff speed at some point there, so good pushing. Okay, well, now let's talk about how far has the box traveled in that 10 seconds. So to figure that out, what I would do is I would say the box starts at some initial x position of 0, and then it's going to reach some x position question mark that I want to find. Now, you can use this final velocity and any of the motion equations to get your answer. But let's pretend like we hadn't already found that velocity and talk about what equation we should use to figure out x. So I'll erase this to give us some room. Now I would think about my initial position is 0. I want to find x question mark, and I look for an equation that has all of these things in it. The equation that has all of those things in it is this one. So I go back to my problem, and I write the equation down. 1/2 at squared plus v naught t plus x naught. So again, I don't actually need to rearrange anything in this equation, which is nice, but I will get rid of some things that are 0. The initial position, x naught, is 0, so I get rid of that. The initial velocity is 0, so I'll get rid of this term. And now my equation just simply becomes x, the distance forward, is half the acceleration with time squared. So half of my acceleration, which I found before, 12 meters per second squared, times 10 seconds squared. Or half of 12, which is 6, times 100, right? Because 10 times 10 is 100, yeah. So half of 12 times 10 times 10 is 600 meters. Okay, great, good job. Let's do another example problem. You are pushing a 100 kilogram moving box with a force of 200 newtons. The kinetic coefficient of friction between the box and the floor is 0.5, while the static coefficient of friction is 0.6. Is the box speeding up, slowing down, or moving with constant velocity? Okay, so let's start by drawing a free body diagram of this box. There's going to be a weight force down, normal force up. You're pushing forward with a force of 200 newtons. And there is, oh, you know what? Actually, I don't know how much friction there is. So let's talk about that. How much friction is there going to be? I know it's going to be mu times normal force because friction is fun. But will there be static or kinetic friction? I'm given the coefficient of both. So how do I decide? Well, I could calculate the static maximum friction and the kinetic friction and compare it to this applied force. But let's take a look at what we're told about the motion of the box before all that. It's moving. If the box is moving, then it does not matter what the maximum static force of friction and the applied force is. If it's moving, then we know there is kinetic friction. So to figure out the kinetic friction, I remember that the weight is equal to the normal force in this problem because the object is not accelerating up or down. And now I can take that 0.5, that's the kinetic coefficient of friction, and multiply that by the weight, or 100 kilograms mass times acceleration due to gravity. So the weight is 1,000 newtons, which means my kinetic friction is 500 newtons. So that tells me that the kinetic friction is actually bigger than my applied force of 200 newtons. So the box, as it moves to the right, it doesn't say that, but I mean, I wrote the problem and it's supposed to say it, moving to the right. The box is moving to the right, but that 200 newtons that you're pushing forward with is not enough to actually keep it in motion. So what happens is that the force of friction overpowers your applied force and the box begins to slow down, meaning there is an acceleration to the left in the opposite direction. So the box is slowing down. Now, let's say that we knew the initial velocity of this box was 10 meters per second. Let's figure out how far it would go before coming to a stop. So how far it would go before coming to a stop. Basically, we're saying at some point, the box is going to reach this place where, well, we don't have to draw the forces on it there. We'll just write this. V equals 0, and I want to figure out x, where it, how far it went. Now, of course, we'd have to write x naught equals 0 to indicate that the box starts at 0 and then reaches this final position x. But let's talk about how we would now move into a kinematic problem to try and figure out how far forward does it go before it stops. Okay, before we can do anything, we have to find out what is this acceleration. And to do that, I'm going to look at the applied force and friction to find the net force. So maybe you can already see it. The net force is going to be your applied force minus friction, or 200 newtons minus 500 newtons. So negative 300 newtons. Well, now I can use that with my equation for net force, mass times acceleration, which I can rearrange to get the acceleration is the net force over the mass. So I take that net force of negative 300 newtons and divide it by the mass, of 100 kilograms. This gives me an acceleration of negative 3 meters per second squared. Now, this acceleration should be negative because my initial velocity... Okay, well, now that I've figured out the acceleration, I'm going to clear some room. And now I'm going to write down some of the information that I've got. So let's think about the given kinematic information. Right, the initial position is 0. I want to find the final position. My initial velocity is 10, and my final velocity is 0. So which equation has all of these things? Well, okay, so let's write down the kinematic information. Initial position is 0. I want to find x. The initial velocity is a positive 10 meters per second, and I want to find the... final velocity is 0, and I want to find the ending position. Okay, so notice that I'm not given time, and that's my clue that I should use the equation without time, or the ain't got no time equation. I get rid of anything that's 0, so the final velocity is 0, the initial position is 0, so 0 equals 2ax plus v naught squared. Then I subtract v naught squared from both sides and divide by 2a, so I can find x, the final position. So to figure out how far forward it goes, I would take that 10 meters per second, the initial velocity, square it, and then divide by 2 times my acceleration. And I have to be careful to use a negative 3 so that I get a positive answer when I put everything together. So this is positive 100 meters per second. I'm sorry, negative, because you square, then you do the negative, over negative 6 meters per second squared, which gives me a positive 16.6 repeating meters. So that's how far forward the box has gone. And it's over.